absolute value graphs and their transformations. First, let's just do a quick refresher on absolute value equations and inequalities. Do the lesson opener, pause, come back when you're done. How'd you do? Pause if you need to and fix your work so that you make sure to learn from any potential mistakes. Next, let's take a look at the absolute value graph. It is one of our parent functions, so we want to get to know it very well. Given the graph of y equals absolute value of x, let's go ahead and fill in our table of values and plot some points. So y equals absolute value of x. If x is -3, y equals absolute value of -3. And we remember that absolute value means always positive. So we're going to get +3 and so on. Fill out that table of values and then let's plot the points. The first point is -3, 3. So let's go ahead over 1, 2, 3, up 1, 2, 3, and so on. -2, 2, and so on. Go ahead and finish the points. These are just some of the points that represent the graph, but of course it is a continuous graph because I could put in what is y when x is 1.5. Well, it's going to be 1.5, right? So I'm going to go ahead and connect the points that we have plotted so far, recognizing that this is a continuous graph, and look at the shape that we get. What do you notice about the graph? It's a V. Absolute value, V, value, absolutely. Okay, so there's a good observation. Absolute value, V. The other thing I noticed is we have a vertex for the V. You know, that point. Where is that point at? Well, it happens to be at 0, 0, at least for the parent function. Next, for axis of symmetry. What's that? Axis of symmetry means that you can fold the graph perfectly and it matches, right? So is there an axis of symmetry someplace that I could fold the paper and both sides would match? Yep. Let's go ahead and plot it. Okay, I noticed that right there on the y-axis, if I folded it over, the two sides of my absolute value graph would meet perfectly. That's my axis of symmetry. And how do I write an axis of symmetry? As a line. Isn't that my dashed line? It's a line. So what is the equation for that? Well, it's a vertical line. It cuts through the x-axis. So I need to say the axis of symmetry is x equals 0. What else do you notice about that? X equals 0? That happened to be the vertex also, my x-coordinate of the vertex. We need to keep an eye on that and see if that's something we should always pay attention to. What about a min or a max? Well, a min or a max is the y value that is the smallest of the entire function or the biggest of the entire function. Do we have a minimum or a maximum on this absolute value graph? Well, yes, I think we do. It doesn't go any lower than this vertex once again. So what is the lowest y value of the parent function y equals absolute value of x? The lowest y value is 0, and it's a minimum because it's the lowest you can go, right? It's the floor. And where does that occur at? Well, it occurs at the x value of 0. And that's what we need to make sure and write. The min or max value is the y coordinate, and where it happens is the x coordinate. Next, let's just go through domain and range. Do you remember those? Domain is all possible inputs or x coordinates, and range is all possible outputs or y coordinates. So taking a look at domain, let's just take a walk along the x-axis. What do you think? So I'm just having a good day. It's kind of sunny out right now. And I look up and I can see the graph. So I keep walking. That means all of these values are in my domain because I can see part of the graph everywhere along that x-axis. Keep walking, keep walking, keep walking. Sure enough, I can see part of the graph everywhere because remember, it extends indefinitely. That's why I have arrows on the ends there. So I can say all real numbers. Any x value I put in will give me an output. The other way I could say it is, what if I get numbers really, really, really small out here? Do you know what that's called? Or what about if my numbers get very large without end? Have you heard of infinity? Exactly. So where do I have x values that work in my equation? All the way from -infinity to infinity and beyond, okay? And notice that I put those in parentheses because we never arrive at infinity or -infinity. It just keeps going and going and going. Next, let's look at our range. So we're gonna take a walk along the y-axis, starting small and getting bigger. So we start low and start walking up. Well, I'm all the way down here. I don't see any graph. So I have no outputs in this area. So like if I'm down here at -5 and I look left and I look right, I don't see any of my absolute value graphs. So that's not part of the range. Keep walking along. When's the first place that I, boom, run into the graph? At y = 0. And then everywhere I go along the y-axis, I look over here, I have graph, I look over here, I have graph. So I know that my values start at 0 and can get bigger. The outputs are y's greater than or equal to 0. Now what about that other little notation that I had over here? Is there a way to do that for the range? Yes, there is. It starts at 0 and it gets bigger and bigger without bound, right? So the y's go on to infinity without stopping, but they only started at 0. So our notation for that is a closed bracket because it can equal 0. That's a value it can equal, all the way into infinity and beyond, which of course it cannot equal, so I use a parenthesis. Now I realize this interval notation is a little new, but don't worry, you're gonna like it and you're gonna be able to use both back and forth. Let's look at our next thought. Given f of x equals the absolute value of x minus 3, what's gonna happen? Well, I know, but let's see if we can get you to know. Here we go. We're gonna plug in a 1. You'll see why in a moment. Or do you wanna take a quick guess what's gonna happen? Because maybe you know. What's that minus 3 gonna do to everything? Well, if I plug in a 1, I'm gonna have f of x, so f of 1 equals absolute value of 1 minus 3, which is absolute value of -2, which is 2. Boom. Go ahead and finish that table of values and let's see what ends up happening to our graph. Did you get what I got? Looks like we still have our absolute value graph, v, parent function, but it has been translated which direction? Yeah, it went to the right 3 units. Did you notice that in the table of values as well? What was the equivalent? So where was my vertex originally? At 0, 0, but now where's my vertex? Oh, it's at 3, 0. So if I track the vertex, here's my vertex to vertex, what's changed? The x coordinate increased by 3 for the equivalent y output value. And sure enough, if I look here at 1, 1, and now I have 4, 1, what's changed? The x coordinate has gotten bigger by 3. All right, this is some good information, and this shows you what our lesson is about today. Transformations. Transformations that we'll work with, and we're just gonna talk about them informally, not formal definitions. We have a translation, which is moving. We can move left, right, or up, down. A dilation refers to changing the shape a little bit, okay? So we're going to stretch or compress. Stretch or compress. With dilations, for our purposes, we're really only going to be talking about vertical stretches and vertical compressions. Later on, we'll talk about horizontal stretches and horizontal compressions. And last, reflection. What's a reflection? Well, you guys like to call it flipped, right? But we're gonna call it reflection and use some good academic vocabulary. It has been flipped, it has been reflected. It can reflect over the x-axis, horizontal axis, or over the y-axis. But what happens if it reflects over the y-axis? We're not gonna notice a change, at least on the parent function absolute value. We'll see it later on. Those are the transformations that we deal with in Algebra 2. You might remember in geometry that you also did rotations, but we don't have that to do in Algebra 2. If you look at number 1 now, A, it says g of x equals the absolute value of x plus 3. I bet you have a good guess what is going to happen. Wanna write it down? What's gonna happen with absolute value of x plus 3?
Did you guess translated left 3 units? You'd totally be right. Check this out. See up here, it was -3, and that shifted our graph to the right. So if it's inside those absolute value bars and we're adding 3, then it's gonna be a shift left or a translation left. Now make sure you're using correct academic language down here, right? You have to tell me the parent function and that it's been translated left 3 units. Remember to be doing that. I should be able to graph based on your description of the transformations. Okay, so do I need to make a table to graph this, or could I kind of just use what I know about these absolute value graphs? Up here, here's my parent function, right? If I'm gonna translate this left 3 units, I'm just gonna move this V this direction 3 units. So we can look at these points on the original parent function and call these our pattern points, where if we start at the vertex and we get our vertex plotted, we can go, okay, well, from the vertex, I go up 1 and over 1 on the left and right side to get the next point. And then I continue up 1, over 1, up 1, over 1 to keep drawing. So on my parent function, my original vertex would be right here at 0, 0. So if I'm translating this graph to the left 3, my new vertex is gonna be at -3, 0. So now I go, okay, my pattern points are from my vertex, I go up 1, over 1. Then I keep going up 1, over 1. So from my vertex, up 1, over 1 on both sides, up 1, over 1 on both sides, and I get that nice solid absolute value V shape. So there's my absolute value graph shifted to the left 3 units. So my vertex, we already see it on our graph, is -3, 0, which means my axis of symmetry is right here at x equals -3. The x coordinate of the vertex. Then this graph has a minimum of my y value, 0 of the vertex, at my x value, -3 of that vertex right here. The domain, well, if I put my little stick figure on this graph, he's gonna be able to see the graph as he walks across the entire x-axis. So my domain is all real numbers, or we could write it in interval notation, -infinity to +infinity. And my range, okay, if I put my little stick figure on this part of the graph and he starts climbing up the graph, he's gonna start to see it at 0, and then he's gonna continue seeing it everywhere after 0. So I could say y is greater than or equal to 0, or I could use interval notation where I put a bracket at 0 because I can see it at 0, and then I continue seeing it all the way to infinity, but we never reach infinity, so a parenthesis on infinity. So let's travel over to this next one. We've got the absolute value of x minus 2 and then -3. So take a moment, predict what you think is gonna happen. What's this -2 gonna do? And what's this -3 outside the absolute value bar is gonna do? Did you say that -2 was gonna be a shift right 2? You would have been spot on if you did. And then that -3 is actually a shift down because it's outside of the absolute value bars. So let's wait a minute and think about this. If we have something going on with the x inside the absolute value bars, so like an x minus or an x plus inside our absolute value, it seems to be that when it's a minus, it's a translation right, but when it's a plus, it's a translation left, which almost seems like backwards in our brain, right? Right usually is positive and left usually is negative. So it's almost like we could think if something happens inside the absolute value bars, it's the opposite of what we think. So inside opposite. Outside though, that -3 really is a shift down 3. So we're headed the negative direction down. So outside's exactly what we think. So if that would have been a +3, it would have been an up 3. So inside opposite, outside same. So y equals absolute value of x is being translated right 2 and down 3. So let's get that vertex plotted first, and then we can use our pattern points to graph the absolute value graph. So right 2, down 3. So it looks like my vertex is right here at 2, -3. So now from my vertex, I'm gonna go up 1, over 1, up 1, over 1 to get my V drawn. So up 1, over 1 on both sides, up 1, over 1 on both sides. So I got my nice solid absolute value graph. Clearly looks like a V, which is what they should look like. So let's go ahead and fill in what we know about this graph. Vertex is 2, -3. Axis of symmetry is x equals 2, which is the same as my x coordinate on my vertex. There's a minimum of that y coordinate, -3, at x equals 2. The domain is all reals, and here's the range this time is a little bit different. If I put my little stick figure on this graph, I actually start to see the graph at -3, and then everywhere after -3. So I could say y is greater than or equal to -3, or I could write an interval notation and put a bracket on -3, and I can continue seeing the graph all the way to infinity. How about you go try the next one? First, identify those transformations, then try to graph it and fill in what you know about the graph. You got this. Absolute value of x plus 1 plus 2. Okay, inside opposite. So we see that plus 1, we should be thinking left 1. So that's a translated left 1. Plus 2, outside same, so plus is gonna be up 2. So I've got my absolute value graph, y equals absolute value x is translated left 1 and up 2. So my vertex is at -1, 2. My axis of symmetry is at x equals -1, because that's my x coordinate of my vertex. Minimum of 2 at x equals 1. The domain is still all reals, and my range this time is y is greater than or equal to 2. Really make sure you're understanding that range. If I put my If I put my little stick figure on my y-axis, because range is my y values, he's not gonna see the graph until he hits 2, and then as he continues walking, he's gonna see it everywhere above 2. So that's why we're saying y is greater than or equal to 2, or you can be using that interval notation, 2 to infinity, with a bracket on my 2.
Think of how much you've learned so far. You already know translations, left, right, up, down. It's really awesome because these rules that we're talking about are going to apply to all of our parent functions that we get to this year.